of the work that's done at the present. I should also mention he did very nice work on the chiral phase transition with Frank Wilczek. In recent years, his focus has been on understanding the structure of the quark gluon plasma near TC, in particular his work on thinking of it as a condensate of Z3 Wilson lines. Anyway, so he's going to talk about his most recent work, which is not exactly in that direction. Fabian Rennecke, I met while he was a graduate student already at Heidelberg University, where he was doing his PhD under the supervision of Jan Pawlowski. Fabian's interest is also in non-perturbative QCD, and we were fortunate to have him as a postdoc at Brookhaven on a DFG fellowship, first working with Rob in our group, and then subsequently with Alexei Swelik in condensed matter physics. So his interests really span many body physics in both QCD and condensed matter systems. His work spans interest in instantons, but he's best known for his clever application of the functional renormalization group methods to many body systems. Currently, he's a long-term staff at Giessen University. So without further ado, we look forward to their talks.
Thank you, Raju.
If any questions, please add it in the chat, and I will either interrupt the speakers or leave it for the end.
Good. Thank you, Raju, for that very nice introduction. So I'm going to tell you today about work which I've done in collaboration with Fabian. So I'll first of all give an overview. The title that I was assigned was Exotic Phases of QCD and Heavy Ion Collisions. And what I'm going to argue is that it's actually not so exotic. Now, one of the fundamental contributions was made of... Yes?
I have two black bars going across the screen near the title and near the corner. Do you know, can you move those?
Is that better?
A little, yes. If you get the last bar a little bit further out, the other one.
That's the stop share.
Oh, that makes,
how's
okay.
that?
That's much better, much better.
That's perfect.
Yeah.
Okay. Was made by Asakawa and Yasaki in '89, but was really given prominence by Krishna Rajagopal, Edward Chiryak, and Misha Stefanov in paper in '98 and follow-up work in '99, and later especially by Misha, where they pointed out that for QCD, that you really expect there could be a true critical point in the phase diagram. And the principal question that I want to raise with you today is how wide is the basin of attraction to the critical endpoint? That is, how close, if it's at some point, some T critical and mu critical, how close do you have to get to that point to see long range correlations? And I'm going to argue that there's other interesting phenomenon going on. They generally go by the term of a Moat spectrum, and I'll explain what that is. It also gives rise to inhomogeneous condensates, which we call chiral spirals. And then if you have pions, as we certainly do in QCD, to the possibility of a phase we call quantum pion liquids. And the interest here is that they can arise in a much wider region of the phase diagram, possibly, than a critical endpoint. So I'm going to give it an introduction, and then Fabian's going to talk in detail about experimental signals of a Moat regime. And the basic point for the experimentalist is you have to measure at low momentum less than the pion mass. And it's admittedly not an easy task, but I think it's possible that there's some very interesting things lurking at low momentum in heavy ion collisions. And I should also mention that if there's time, there's recent work which I did with Martin Leisure, Robert Connick, and Alexei Swelik on the solution of nuclear matter in 1+1 dimensions. But we'll see how the time goes. Okay. So let me first of all review stuff that should be very familiar to all of you, just so it's clear that we understand we're talking about the same thing. So this should be just a review slide. So let's consider a field phi where we take the sigma meson, which is spin parity 0 plus, and combine it with the pion. And then the SU2 left cross SU2 right symmetry gives us an O4 chiral symmetry. And I'll assume that the axial U1 symmetry is broken by the temperatures and chemical potentials of interest. So we can write down a simple effect of Lagrange. We have a kinetic term, a mass term, and a quartic coupling. And normally we take this coupling to be positive, and we get a phase transition then as the mass squared goes to 0. When the mass vanishes, we have infinite correlation length, and this is a second order transition. But what we can also do is we can let this coupling be negative. Now, if the coupling's negative, we have to do something to make sure the bottom doesn't fall out of the potential, and we have to add a term that's of sixth order in the field. But that's certainly expected to be there. And if we do so, what we're going to have is a first order transition for some positive m squared. And we can then ask what happens where both the coupling and the mass squared vanish. That turns out to be a tricritical point. Now, this was all for 0 pion mass. What happens with non-zero pion mass is that the second order line becomes a crossover, and the tricritical point becomes a critical endpoint. So again, as I said, this is all standard stuff. This is nothing new. My principal question is, how wide is the basin of attraction for a critical endpoint? Well, what happens, you normally see here, if you take lambda positive as m squared goes to 0, in the chiral limit, all of these fields become massless, the sigma and the pion. The sigma is massive in the broken phase, the pion is massless, they come together, and then above TC, they're both massive. At the critical endpoint, it's a little odd. The pion remains massive, even in the chiral limit, and it's only the sigma that gets light, because it's associated with a Z2 universality class. So you would think naively that you at least have to have the sigma to get lighter than the pion. But as we well know, the signal for the sigma is not easy to see because it's a heavy state. And more to the point, it's also very broad. And that's what matters, both the mass and the width. And you have to get this to be lighter than the pion, which already is light. And so the basic point is that it's hard making a heavy field light. And this gives you a relatively narrow basin of attraction. This is based upon work which Fabian will talk about later in the talk. So if you have questions about this, just wait, and Fabian will address that. Okay. At non-zero temperature and chemical potential, Lorentzian invariance is lost. And so we can actually do something more interesting. We can take an effective Lagrangian where we have 2 time derivatives, and we can only take 2 time derivatives, so we lose causality and terrible things happen. But for the term with 2 spatial derivatives, we can let the factor in front, the wave function or normalization, z, be arbitrary. And in fact, we can let it be negative. Now, if we let it be negative, like with the potential, we have to add something to stabilize the theory. And we can add a non-renormalizable term involving 4 spatial derivatives. And we take the usual potential. Now, you might think this is a peculiar thing to do, but it's in fact very common in condensed matter systems, such as smectic liquid crystals, and there's a whole raft of systems. And you might ask, well, wait a second, why is this quartic coupling? Why is this wave function normalization? Why are they flipping sign? It's not obvious. It doesn't happen at 0 chemical potential. It's really special to non-zero chemical potential, and basically it's due to the fact that fermion loops have a minus sign. In any case, I'll show you models where it certainly happens. Now, when this factor z is less than 0, well, if I look at this, this is going to give me energy squared, and it's easy to read off what the dispersion relation is. I get the usual mass squared, momentum squared, and now I get momentum to the 4th. And if this is negative, what happens is that the dispersion relation goes down and then up. So it has a minimum at non-zero spatial momentum. This is what we mean by a moat. And if you have this, you can see that the theory would like to do something. It's kind of funny. as you go faster, the particle gets lighter. And it would generally like to have condensates which vary in space. But another thing that's obvious is that for this kind of spectrum, the fluctuations will be largest at non-zero momentum. This is versus a critical endpoint where fields become massless, and so the fluctuations are largest at zero momentum. Now, there's a simple example of a soluble model that illustrates this. This is the Gros-Neveu model. Admittedly, it's only in 1+1 dimensions, but it's asymptotically free. It's a model of chiral symmetry breaking, and more to the point, it's soluble as the number of fermion flavors goes to infinity. This is Lagrangian. G squared is dimensionless coupling constant, which undergoes dimensional transmutation. And if you look at the phase diagram in the plane of temperature along the y-axis and chemical potential along the x-axis, you have the usual, in vacuum, you have a phase with spontaneous breaking of a Z2 chiral symmetry. And at high temperature, you always restore the chiral symmetry. So this blue line is a second order phase boundary. But there's something else that happens that's called the chiral kink. And in this phase, at low temperature and high chemical potential, psi bar psi is always locally non-zero, but it oscillates in sign. So as you go along the x-axis, it goes down, then up, then down, and there's some period that's related to the chemical potential. Notice that there is, in fact, no first-order transition. You have a Lifshitz point where this factor Z vanishes, but there's no critical point that arises in this model. That's perhaps special to 1+1 dimensions, but it's a matter of concern. It'd be nice finding a toy model that exhibited the phenomena we expect to find in 3+1 dimensions. And I should mention, this is a diagram that was done by Adrian Königstein, Panulo, Reschenberger, Winchtel, and Steil from Frankfurt. They're a group of graduate students at Frankfurt. And what they also did is they plotted not just the temperature and chemical potential, that they plotted this coefficient Z of the term that's quadratic in the spatial derivatives. So here, blue is the usual dispersion relation. It's monotonically increasing. So as you'd expect, the usual, well, certainly at mu equals 0, it's always positive. It's positive for low mu. It's always positive at high T. But there's a very wide region in which it's negative. So again, this is the phase with chiral kinks, the hatched region. But you see there's this large red region where you restore the chiral symmetry, but it still has this non-monotonic dispersion relation. So it does lead to chiral kinks at small mu, but as you can see, there's a wide region where something else is going on. And the question is, could we find experimental signals of that sort of thing? I should also mention that besides for Gros-Neveu model in 1+1 dimensions, Neri-An, and also Michel Bubala, Kurth, Mark Wagner at Frankfurt, Bubala's of course in Darmstadt, and Winstell, have shown that this doesn't happen for the Gros-Neveu in 2+1 dimensions. I think this is a matter of looking at a more general model. Okay, there's something else interesting that goes on.
Rob, you froze up. Rob, can you hear us?
Yeah, I can hear you.
Yeah, you froze briefly there.
I'm at work on Ethernet. I can't do anything.
Okay,
better.
So just okay, better now.
Can you repeat what you said in your last two sentences?
Yeah. In the Gros-Neveu model, you only break a Z2 symmetry. You don't have Goldstone bosons. So with Semyon Velgashev and Alexei Tsvelik, we considered a model where you have pions or you have Goldstone bosons. So we took a very general Lagrangian where you have an infinite number of higher derivative spatial terms, an infinite number of higher order potential terms. Now this, however, is not the most general model, but it's what we could solve for. And we assume that these Z's and V's are such that you have a chiral spiral. So this is now, it's different from a kink. As you go along, phi has an expectation value, but it rotates between, say, the sigma and pi3 direction. And then what you can show is, well, if you have Goldstone bosons, you figure the energy has to vanish somewhere. And what you can show is that it vanishes at non-zero momentum. And we believe this has a fundamental explanation that at least I am too dim to understand. But what happens is, if it vanishes at a non-zero momentum, that means about this momentum P naught, it's P minus P naught squared. And if you have a simple tadpole diagram, you're going to get d cubed P upstairs, P minus P naught squared downstairs. But then this is about P naught, so you're going to have a linear infrared divergence. And we argue that this disorders the system and produces what we term a quantum pion liquid in analogy to a quantum spin liquid. We can in fact show this rigorously at infinite n. And we conjecture there are no chiral spirals for any ON. What this means is that it's a disordered system, but it's an unusual disordered system. Okay. And with that, I leave it to Fabian, who's going to talk about Moat regimes. And let me see if I can. Hello?
Yes, we can hear you.
Oh, okay.
So there's a question from Thomas saying,
Schaefer?
isn't this the old pion, Thomas Schaefer, isn't this the old pion condensation scenario?
No. No. The pion condensation scenario is something where you have a, it basically is the chiral spiral. You have a condensate in one dimension along a given axis. That has a logarithmic infrared divergence. There's no true long range order, but only logarithmically. This is not that. This is something qualitatively new. Okay, I think
Peter also has a question if it's quick.
I just would like to ask, I mean, in QCD, I assume when you want to make Z negative, you need some baryon groups. And is there any range of parameters where you think it can happen?
Fabian will talk about that now.
All right.
Okay, very good.
And
okay,
I'm going to have to hang up because I can't figure out how to stop sharing my screen. So I'm just going to exit and then I'll rejoin. Okay?
Okay. Fabian? Okay, very good. Can you share your screen?
Raju, Peter has a question, I guess.
No, Peter already
asked
his question.
I will lower my hand.
Fabian, can you hear us? Fabian? Fabian. I don't know if anyone else can hear him, but I can.
Fabian, we cannot hear you. Can you try to?
Do you hear me now?
Yes, we can. Okay.
Okay. Somehow I had to change the audio input. Okay, weird. But you hear me okay?
Yes. No.
Okay. Very good. So yeah. You see my slide?
We see something saying Moat regimes. Yes.
Yeah. Okay. That's a slide.
Okay. Good.
Okay. All right. Yeah. Thanks a lot for having me here. That's the second part of this duet. Before I come to the experimental signatures, as Rob has announced, I will highlight some more points about Moat regimes and maybe also reiterate some points that Rob has made. So first of all, at least to me, it's always helpful to have a heuristic picture, and in context of the mode. So whenever you have some spatial oscillation with the wave number k0, if you look at this in momentum space, you find a sharply centered peak around this wave number. And correspondingly, whenever particles are subject to some sort of spatial modulation, they are favored to have a finite momentum related to this wave number. And in this case, then they will typically get such a mode energy dispersion. So this is what Rob has already written down in a slightly different notation. So my W is his 1 over m squared, okay? And this mode regime is when Z is smaller than 0, this wave function renormalization. Okay, and this is something that's typical for inhomogeneous phases or the, say, the quantum Pion liquid that Rob has just introduced. So where can we find these mode regimes? So Rob has argued that we need finite density, and you certainly see it in Gros-Neveu in 1+1 dimensions, and in this ON model in the large N limit that Rob has discussed. So, but what's with QCD? That's, I guess, for us the interesting case. So here I show a result of a computation in QCD that we have done not too long ago. So that's not a model computation, that's in QCD. And here it's a phase diagram in the plane of temperature and baryon chemical potential. And this red dashed line is the chiral crossover. The red dot is a critical endpoint. Then these dots here are lattice results for the crossover. So this here are errors. They are not the width of the crossover. Here the red shaded region just denotes the width. And then here to the right, we didn't even bother to compute the phase diagram because we have reasons to believe that at around mu b over t larger than 4, we might have large systematic errors in our computation. So all that is kind of to the right of this dashed line here should be taken with a grain of salt. But nonetheless, what we find in our computation is that up here, we indeed find an extended region where this wave function renormalization, the Z factor, is smaller than 0. So while we still have to scrutinize this, it's, let's call it a first indication that there might be such a mode regime in QCD. So then what does this actually mean to have this mode? So first of all, in this mode regime, right here, if you look at the energy dispersion, it looks like this mode that Rob has described with the minimum at some non-zero momentum. And crucially, it's positive everywhere. So even at the minimum, there's still this finite energy gap. But you could now imagine, say, you go to lower temperatures and higher chemical potentials, and this gap might close. And if you have 0 energy somewhere, in this case, it indicates that you have an instability towards the formation of an inhomogeneous condensate. So your energy vanishes at K0, which means that it doesn't cost any energy to produce particle with this particular momentum. So there will be a condensate. And a basic example of such a condensate, this is also what Rob mentioned, is ON chiral spiral. So if for 2-flavor QCD, for instance, this would be O4, and then your field would just be the spectra with the sigma meson and the 3 pions. And the chiral spiral would then be a condensate which kind of oscillates between the neutral pion and the sigma meson with a wave number K0. And importantly, it's only in one spatial dimension. So here it's just propagating in that direction, if you wish. And Rob has shown that, for instance, in a Gros-Neveu model in 1+1 dimension, you can then compute the phase diagram based on condensates, maybe not exactly this one, but like this. But there are also other models if you allow for such condensates. And here I show an example for a quark meson model in 3+1 dimensions, which has been computed in the mean field approximation in the chiral limit. So this dashed line here is the second order chiral transition. Then this dot here is the Lifshitz point that Rob mentioned. And then there is indeed here this red region, orange region, which is an inhomogeneous phase. So let's call this now option 1 of what a mode might mean. Namely, it could be a precursor for an inhomogeneous phase. So then, for instance, down here, this is suggested by computations like these, that then instead of, say, the conventional first order phase transition you might expect after the critical endpoint, there could be a chiral condensate, an inhomogeneous chiral condensate. But there could also be at larger densities, there could also be a crystalline superconductor, for instance. Or there could be both. Well, we don't know. That's why in this kind of cartoon phase diagram, all this is kind of marked gray. Okay, this is option 1. But as Rob has already indicated, that's not the whole story, because well, these inhomogeneous phases are mostly studied in mean field, but there's spontaneous symmetry breaking in the system, so you will get massless Goldstone modes. And since they are masses, or at least very light, their fluctuation must be relevant. And in case of inhomogeneous phases, there are two types of spontaneous symmetry breaking. The first is the spontaneous breaking of your continuous spatial symmetries, so like rotations and translations and so on, down to discrete ones. So with this one-dimensional condensate I've shown you, obviously in this direction, you only have a discrete translation symmetry left. Okay. But then there could also be global flavor symmetries broken. Again, on the example of the chiral spiral, you break ON down to ON minus 2. So now kind of an important ingredient is that it has been argued that at least at not really long-dimensional modulations are actually favored against higher dimensional ones. So that it's favored to have such condensates which only kind of propagate in one spatial direction and not depend also on X and Y, for instance. And in this case, the Goldstone bosons from spatial symmetry breaking, which are then known, for instance, as phonons, lead to the so-called Landau-Payals instability of these one-dimensional inhomogeneous condensates. In particular, these fluctuations of these Goldstones from spatial symmetry breaking lead to logarithmic divergences. This is what Rob mentioned in the context of the Pion condensate. And then these one-dimensional condensates are destroyed by fluctuations and the system is disordered. However, in an ordinary disordered system, if you look at the correlation functions at large distances, they typically fall off exponentially. However, with these logarithmic divergences, it can happen that there's an algebraic instead of exponential decay of correlations. And in this case, this is then called a quasi-long-range order. And in condensed matter physics, for instance, this is something familiar in liquid crystals, for instance. So let's call this now option 2 of what this mode might imply, namely that it's a precursor for a liquid crystal-like phase in QCD. But that's still not all, and that's what Rob has already explained, so I don't have to say much about it, because there can also be Goldstone bosons from your flavor symmetry breaking. And in this case, the situation is in a sense even worse, because this is what he indicated. You may now imagine, for instance, you have your chiral spiral, and then you have fluctuations in transverse direction. So these are the fluctuations of your Goldstone modes. Then these are the directions where the zeros are here in the condensate. And the propagator of these Goldstone modes has a double pole at some finite momentum k0. And if you then compute quantum corrections in a theory with such a propagator, you find that the corresponding fluctuations lead to linear infrared divergences at finite temperature, and this is true in any dimension. And so in this case, these Goldstone fluctuations also disorder the system. There are no inhomogeneous phases when you have Goldstone bosons. So for this chiral spiral, n has to be larger than 2, obviously, otherwise you don't have any Goldstones. And since it's a linear infrared divergence, as opposed to the Landau-Payals instability, there's not even quasi-long-range order. And Rob has mentioned so far the only thing that they have been able to do was to prove this rigorously in large n. And then what do you have instead? There's this quantum Pion liquid that Rob already mentioned. So you have a disordered phase, but you have this mode energy spectrum, which is everywhere positive, and there's an energy gap that is dynamically generated. And you still have spatial modulations in the system as a result of the structure of this Goldstone propagator, then if you take into account fluctuations, that at large distances, for instance, the 2-point correlation, instead of just falling off exponentially, has this periodic modulation. So this is now option 3. The mode signals that there's a quantum Pion liquid in QCD. So let me just kind of summarize this. The mode could basically mean one of 3 things. First, we could have an inhomogeneous phase, but this is presumably only possible if there are no Goldstone bosons whatsoever. Option 2 is we could have something like a liquid crystal, and this is only possible if there are only Goldstones from spatial symmetry breaking. And option 3 is if we have also Goldstones from flavor symmetry breaking, then we have a quantum Pion liquid. And all these phases are expected where we would also kind of normally expect these inhomogeneous phases. So maybe somewhere here in the phase there. But as I said, we don't know yet. So there are certainly interesting stuff going on here in the context of the mode. So then the obvious question is, what are the signatures of such regimes in heavy ion collisions? And that's based on quite recent work with Rob. So how do we probe the phase diagram? I don't have to explain much here with this audience, I guess. We do a heavy ion collision. So we smash heavy ions. And then after a pre-equilibrium phase, the evolution of the system can be described by hydrodynamics. And then as it cools and expands, it traverses the phase diagram from a QGP phase into a hadronic phase. And then eventually the system is so dilute that kind of interaction cease and the particles more or less free stream to the detector. So if you're interested in the phase diagram, you want to look for imprints on this freeze-out surface, because in some sense you map the freeze-out surface onto your detector. Okay. Now we are interested in finite chemical potential or large chemical potential. Even how do we do that? Well, we do beam energy scans. So the smaller the energy we use for the collision, the larger is the chemical potential. And here I show our phase diagram again, and I just added to guide the eye kind of some freeze-out points. The blue ones are from RHIC data, and these greenish points here are from lower energy experiments at SBS and AGS. And in particular, at lower energies, you see that we are likely producing systems that are, at least during some stages in their evolution, would actually traverse such a mode regime. And then if there would be something interesting down here, maybe also lie within these phases. And this is in particular interesting because STAR has now, they have their fixed target program. Then there's Hades at GSI, and then these future experiments like CBM and FAIR, but also other facilities like JPark, NICA, and HIAF, who will all probe the, let's call it this interesting, maybe exotic region of the phase diagram with fairly low energies. So then it's kind of all the more pressing, I guess, to ask what the signatures of mode regimes are in heavy ion collisions. And for that, the main idea is actually very basic. So we have learned that these modes arise in regimes with spatial modulations in the phase diagram at large chemical potential. And the characteristic feature is that particles in this regime have minimal energy at some non-zero momentum. So it's kind of intuitively clear that particle production at this particular momentum will be enhanced because it's easier to produce the particles that carry this particular momentum. So what we want to do is we look for signatures in the momentum dependence of particle numbers and their correlations. So this is kind of, this is the punchline. So this is the punchline, basically with more detail on the following slides. So first of all, also something that I don't really have to explain to this audience. Obviously, particle number, we all know that particle number distributions are actually observables. I'm just saying that because now average particle numbers, particle spectra, and particle correlations are something that we, or the experimentalists already know how to measure. So this is something realistic to look at. And I've mentioned that we have to look at the freeze out. So, and one typically assumes that particles freeze out, for instance, at a certain temperature or at a certain energy density. And by fixing the temperature in your kind of 4D expanding spacetime, you then slice out a 3D hypersurface, and this is a freeze out surface. And this is always true. In our case, it's more reasonable maybe to talk not about the kinetic freeze out temperature, but say the chemical freeze out temperature. Or really any temperature, then you always slice out some surface. And the freeze-out surface in this case, here's just an example from a hydro simulation in the plane of proper time and radial coordinate. It looks something like this. And these arrows here, their magnitude denotes the size and the direction of the fluid velocity on this freeze-out surface. So to pose a little bit more precisely, what we want to understand is how does the mode regime affect particles on the surface. So we need to compute And how do we compute this? Basically with something like the well-known Cooper-Frye formula. So what are the ingredients? So first of all, we need to know the probability of finding a particle with a certain momentum. And this is in general given by the Wigner function. And if you assume thermal equilibrium, the Wigner function is just given by the spectral function of a particle and the thermal distribution, which for bosons would just be the Bose-Einstein distribution. Then, since these particles are just, they travel along the expanding medium on the freeze-out surface, they are boosted with the corresponding fluid velocity. If we consider the energy and the spatial momentum, we always have to consider the boosted coordinates. So, and then, yeah.
Sorry to interrupt you. There's a question from Uli. Aren't the momentum distribution, the Moat signal, frozen out at kinetic rather than chemical decoupling?
Well, you would, you would freeze out the momentum distributions at chemical freeze out, obviously. But the thing is that the Moat regime is something that still kind of is a property of an interacting medium. So I guess if the system is so dilute and the density is kind of low, then you would already be in a phase which is not the Moat phase anymore, right? So you would, that's a very good point. So I guess realistically, you want to compute kind of the particle spectra on a surface where you are in the Moat regime, and then you need some subsequent kind of methods to propagate this then onto the kinetic freeze out and then see what the signatures are. So that would be kind of a more elaborate version to look for this. But you're right. But I mean,
so you're right. If this is a medium effect that goes away when the system decouples, then of course the danger is that everything gets washed out by the processes that drive the system to decouple, and you will not left with anything. So does the Moat signature also have a signature in the particle yields integrated over momentum?
So integrated over momentum, I'm not sure. I wouldn't think so. So you would need to, this is what I'm going to show you, need to have a differential, say as a function of PT, then you can see something.
Yeah, but I don't think it's useful to plot the effect of the Moat on the momentum distribution on a surface that is not the final freeze-out surface, because it may get completely washed out until freeze-out.
Yeah, that's a fair point. You in the end, you need some, a proper kind of phenomenological simulation of the system, and then so basically, the idea is that at some point you will produce particles with which are favored to have this specific momentum related to the wave number of your spatial modulation. And then these particles will be there. And then the question is, the system will at some point leave the Moat regime. And then the question is obviously, will all these effects be washed out or not? And that's a question I guess we are always facing, because you also have the problem with, say, the long-range correlations you see in a critical point, right? So it's always, that's always a question of then the detailed phenomenological simulation that we don't know yet.
Yeah, please continue.
There's another question, I think. Oh, okay. Okay, yeah, okay.
Yeah.
I continue. Okay, so if we know the probability distribution to find a particle, basically, if we integrate this over momentum, we get something like a particle number current. And if we then integrate the current over the surface, we get the number of particles on the surface. So this is shown here. This is now the particle number current density. This is this Wigner function. There's a theta function to ensure positive energy. And then it's a density T, so it's only integrated over P0. And then this current density is integrated over the freeze-out surface, and then you get particle spectrum. So it's just the particle number differential in your spatial momenta. And if you were in the free theory in vacuum and you just insert the corresponding spectral function here, you just recover the well familiar Cooper-Frye formula. So this is kind of a version which takes into account the spectral function, in medium spectral function, if you wish. Okay, so now we can compute the spectrum. What are the ingredients we need? We need a spectral function. We need to know the fluid velocity on the freeze-out surface, and we need to know the freeze-out surface itself, because we want to integrate over it. So, and I will just use kind of very simple models to show the general structure. So nothing I will show here will in any way be quantitative. So for particles in the Moat regime, I basically used the free version of the model that Rob has introduced. So I just write it down here again. So Rob has already explained this. And if you compute the spectral function for such a theory, you find something that looks like an ordinary vacuum spectral function. So P0 squared minus energy squared. But this energy is now this Moat energy dispersion. So it's a bit more general. And also, I mean, Rob also said this, because of the p to the fourth term, you break boosted symmetry. But that's okay. You are in a medium anyway. Okay, and then for the fluid velocity and the freeze-out surface, you want to get this from hydro, and of course you want to do this actually self-consistently. You know, you want to derive the equation of state for something like this, and then use this to evolve your hydro. We don't have this available yet, so also here I just use very simple models that you can more or less do this all analytically. So first of all, we assume a boost invariant and isotropic in transverse direction freeze out, and which happens at the fixed temperature and some fixed proper time. So our freeze out surface in this picture here would just be a straight line until some maximal radial size of the system. Okay, and then for the fluid velocity, we use the blast wave approximation, which, in addition to the assumptions I've already mentioned for the freeze-out surface, you say that your radial velocity is proportional to the radial distance. So if you integrate this, you see that the radial size of your system grows exponentially in time. So that's why it's called a blast. So this is models. So we need some model parameters, and we basically just kind of pick some beam energy, say 5 GeV, and then look at statistical model fits. That would be a freeze-out chemical potential of like 536 MeV, which would then be something where, if you remember the phase diagram I've shown you, that would create a system that would traverse the Moat regime that find indications for in QCD. And then there are also some blast wave parameters. We take some from blast wave fits, so the average velocity, maximal radius, radial size, and the freeze-out proper time. So these are just some parameters. Later on, I also use some other thermodynamic quantities, and to be kind of consistent with these numbers here, I also take then a hadron resonance gas. And the mode parameters are basically just purely illustrative. When Z is negative, I just pick basically a W to ensure that the energy is still positive everywhere. And yeah, that's kind of for illustration. And with this, we can look at the transverse momentum spectrum. And I compare this now, the normal phase are the grain lines to the Moat phase or Moat regime, which are the yellow lines. So here's the particle spectrum as a function of PT. And first, if you're in the ordinary phase where your dispersion has just a Z factor of 1 and W is 0, then you just find what you see, this monotonically decreasing spectrum. If you say you're still in the normal phase, but Z decreases, then this spectrum becomes more shallow. But now if you enter the Moat regime, it first increases with PT and then decreases, and you can find these peaks here in between. So this is kind of as intuitively expected, that you find that particle production is enhanced at some non-zero momentum. And in fact, the location of this peak in PT is directly related to the wave number of the underlying spatial modulations, basically the boosted wave number. So that's a signature in the particle spectrum, but we can also look at correlations. So obviously, we expect them also to be sensitive to in-medium modifications. And in general, these correlations are difficult to compute, because if you have systems with long-range correlations, with long-range order, they are sensitive to genuine multi-particle correlations. This is why, say, studying the critical endpoint is so hard. But these Moat regimes so far it's just a disordered phase. So maybe we get away with studying single particle correlations to capture the relevant features. And then you can actually use the Cooper-Frye formula to compute correlation. So here I show a very generic n particle correlation. These are just the kind of a product of spectra of your n particles labeled from 1 to n. And there's some average. I will explain this on the next slide. And then you just have kind of an integral over a freeze-out surface for each of your particle. And then you have the Wigner function for each of your particle. And then again, this is averaged. So
Fabian, there's a question in the chat from Bernd Müller. Which particles show enhancement at non-zero PT, only pions or also nucleons?
So from what I can tell now, it will certainly be pions, but I don't see any particular reason, excuse me, why it shouldn't also be nucleons, but we haven't studied this. But yeah, I don't see why nucleons should not also be sensitive to this, but I'm not quite sure. Okay, so if you have this correlation now, if you have some fluctuations, for instance, in your thermodynamic quantities, they lead to fluctuations of your Wigner function, and then this gives rise to some non-trivial correlations. Okay, and here I only consider small fluctuations in the temperature, the baryon chemical potential, and the fluid velocity, and I sum this all up into this. I put this all into this thermodynamic quantity kappa. And then, for instance, a 2-point correlation of your thermodynamic fluctuations then gives rise to some 2-point correlation of your Wigner functions, and then you get the 2-particle correlation. Okay, that's kind of the basic picture. But now, of course, kind of the subtle point is, if you wish, what's this average? And here we just use a thermodynamic average, and thermodynamic average has different configurations with the change in entropy due to fluctuations. So this is the very basic formalism. You can just look it up and say the book by Landau and Lifshitz on statistical physics. Here we look at the entropy current or entropy density current, because we are in a curved space-time. And then we can just write down a generating function for thermodynamic correlations. So this is W of J. It basically is a path integral, but you now integrate over your thermodynamic variables. And then instead of the action in the exponential, you have an integral over the freeze-out surface, your change in the entropy current, and then you insert sources for your thermodynamic fluctuations. And just that's something that just comes out of the formalism. There's this vector that is normal to your freeze-out surface. And then you can just, when you know this thing, you can just take derivatives with respect to these sources, put them to 0, and then you get n particle correlation functions. So now you want to know how this thing looks. And again, for simplicity, let's assume that we are in an ideal fluid and compute the change of entropy with only Gaussian fluctuations. And then what you find is that this delta S mu then looks like this. So it's just quadratic in your thermodynamic fields, and it has this kernel here, the fluctuation matrix, which I show here. So if you forget about these U's and just look at this 2x2 corner here, this is exactly what you find in Landau-Lifshitz. So S is the entropy, N is the baryon density, and this is just standard stuff. But now we also have, we are on this freeze-out surface, and we have the fluctuating fluid velocity. So there's this U hat entering, which is the projection of the fluid velocity normal to the freeze-out surface. And then there are other contributions that come from the fluid velocity also fluctuating. Okay, and then now if we now want to use this to compute something, I already mentioned I just use a hadron resonance gas to compute these thermodynamic quantities. Okay, and as I said, only Gaussian fluctuations. And in this case, the only non-trivial correlation function is the 2-point function. Everything else would be just products of 2-point functions. That's just Wick's theorem. So you get this 2-point function here for your 2 particles, 1 and 2, and you get this kind of unwieldy formula. Here's your fluctuation matrix. And just one thing I want to highlight here, there's only one integral over a freeze-out surface left. I've shown you that. I mean, if you just write this down naively, you have an integration over a freeze-out surface for each of your participating particles. Now there's just one left, and the reason is that these fluctuations are strictly local. And then we can look at the normalized two-particle correlation. So it's the two-particle correlation normalized by the spectra of your individual particles. And this is the result in the normal phase as a function of PT of particle 1 and PT of particle 2. And on the scale I've shown you, this is flat and boring. And as I said, this is the normal phase. So this would be the situation where Z is 0, Z is 1, and W is 0. Now, if you look in the Moat regime, that looks quite different because there's now this pronounced peak appearing here, again, at finite PT, and also these two ridges. And as for the spectrum, the location of this peak and the ridges is related again to the wave number of the spatial modulation. And if you compare the magnitude here at the peak with the corresponding magnitude in the normal phase, you see that it's an enhancement by 2 orders of magnitude. Of course, this is all within these approximations, but the spectrum I've shown is also within the same approximation. In the spectrum, everything here was on the same order of magnitude. And in this in the 2-point correlation, it's already an enhancement of 2 orders of magnitude. So it is kind of, I would expect then these signatures are way more pronounced in higher order correlation functions. So this is then what we would expect a signature of a Moat regime would look like. And so this brings me kind of to the summary of this part. Moats arise in regimes with spatial modulations. We expect them to occur at large baryon chemical potentials. They could be precursors for inhomogeneous or liquid crystal-like or quantum Pion liquid phases, where Rob has introduced the quantum Pion liquid. And one take-home message in this context is certainly that quantum fluctuations are crucial. And then the intuitive kind of result is that we find enhanced particle production at non-zero momentum. And as a result, there will be characteristic peaks and ridges in particle spectra and correlation. So I guess with this, we in principle have the opportunity to discover these novel exotic phases with low energy heavy ion collisions by doing these differential measurements of particles and their correlations. And as Rob has already mentioned, the expected momenta should be somewhere below, say, the Pion mass. So it would be really small momenta that are relevant here. And I guess I made this abundantly clear. So far, what we have is a basic description of the qualitative effects. And then, of course, the next step would be to work even harder to get a more qualitative picture of what's going on. And I don't know if Rob wanted to continue with the one. I guess we still have some time, right? Rob, are you there?
About 5 minutes.
Yeah, no, I'm here. I don't know if people want to discuss. I can go over it briefly.
Yeah, you have 5 minutes, so we can do that. 5 minutes.
Okay, then I stop sharing, and you can share again.
Okay, let me just bring it up and go to the relevant. Okay, just give me a second. Sorry for that. Okay. Presentation. Okay. Share screen. And then you want me to move this and that. Okay. Can you hear me?
Yes. So,
yeah.
You have about
so in 5 minutes, I'll just give you a very brief idea of some work that I did in collaboration with condensed matter theorists here at Brookhaven. Robert, in particular, Martin Laget, Robert Connick, and Alexei Tsvelix. And the point is that using in 1+1 dimensions, you know, at Hoof showed that you can solve for QCD at large in C for heavy quarks. And Brock Bringholz in 2009 showed that you get in fact, a chiral kink, a kink crystal at non-zero chemical potential. What we were able to use is to solve for a small number of colors and a number of flavors, arbitrary number of flavors, using a clever choice of gauge due to Varouche-Belluni. And what you can show is that, let's take the case of a single flavor. You can use abelian bosonization and reduce QCD to the number of colors minus 1 Stein-Gordon models. And then they can use all these tricks that they have, conformal field theory, thermodynamic beta ansatz. But given the audience and for the reasons of time, let me just skip ahead. For an SUN gauge field, you have NC minus 1 coupled Stein-Gordon models. You have kinks, you have anti-kinks, you have breathers, which are combinations of kinks and anti-kinks. It's a complicated spectrum. It's 1 + 1 dimensions, but it's a confining theory, and it's involved. But if you just look at the low energy excitations near the Fermi surface, then you can use bosonization. And bosonization tells you that the time-like component, the fermion current, is the spatial derivative of a scalar field phi, which is a periodic variable. And then you can write down, show that all of these complications, if you just look at the U1 excitations, that you have an effective Lagrangian involving this field phi and a Stein-Gordon model. And then what they can show is that as you go to larger and larger distances for the excitations near the Fermi surface, that the theory runs to what's known as a Luttinger liquid. And this is why I wanted to show it to you, because your condensed matter colleagues have probably mentioned Luttinger liquid, and you wonder, what is that? It's actually really simple. It's a free massless scalar field in 1 + 1 dimensions. It doesn't propagate at the speed of light. There's a factor of the Fermi velocity here, 1 over VF in front of the time-like term with time derivatives, VF with the term with the spatial derivatives. And there's an overall constant K. Now you might say K, oh, I can just renormalize that away by shifting phi by an overall scale. But as I said, it's a periodic variable. So that constant in front, K, is physical. That's a function of the chemical potential mu. It's known as the Luttinger parameter. The Fermi velocity is also a function of mu. And what you can show is that as mu goes to m, this is the m is the mass of the lightest soliton. It's where you'd expect the Fermi surface first to form. That k goes to 1, well, that's kind of boring. And the Fermi velocity goes to 0, so this thing decouples. As mu goes to infinity, you then get Vf goes to 1 and k goes to 1. And Martin and Alexei were able to use the thermodynamic beta ansatz to solve for arbitrary mu. Well, you might say, who cares? This is 1 + 1 dimensions. But it's really interesting because you start with fermions with the Fermi surface, and because of strong infrared interactions, in this case confinement, we don't have any fermions left near the Fermi surface. We just have U1 bosons. And this is, in fact, the prototypical example of a non-Fermi liquid. A Fermi liquid is where you have well-defined quasi-particles near the Fermi surface, so their width is much less than the energy. For a non-Fermi liquid, the width is on the order of the energy. And this is why people are excited about ADS and condensed matter, because it gives you many examples where this can happen. Now, what does this have to do with QCD? Well, Larry McLaren and I argued some time ago that if you go to large NC, that you naturally have a region where the deconfinement line is basically flat until very large chemical potentials. And in particular, for reasons of time, I won't go through. If you're in this region at large NC, we believe that the Fermi surface is covered with many small patches. And in that case, it looks effectively 3 dimensions. So mu is much bigger than lambda QCD, and you get patches where the theory looks 1-dimensional. And we believe this kind of non-Fermi liquid can arise. Now, you certainly might say, well, this is, NC equals 3 and F equals 3. Who are you kidding? But there's been recent work done by in Swansea by Simon Hans, Janivar Skellerud, and collaborators, and also recently by a group in Moscow, Bornyakov, Baguta, and others. In fact, the paper appeared recently that shows even for two colors where they can do numerical simulations, the fermion determinant is not imaginary, you don't have a sign problem, that you have this kind of quarkionic behavior. So we believe that, in fact, it's very possible that occurs at high density. This would be for cold nuclear matter, not accessible in heavy ions. And so that's why I left it till the last. But it would certainly be relevant to neutron stars. And in particular, it would tell you that the transport properties of a neutron star at high densities is not described by that of fermionic quasiparticles, but that of bosonic. And one could imagine constructing effective theories to describe that. And with that, I'll stop and thank you.
Okay, thank you very much, both to Rob and Fabian for this very nice talk. So I think the floor is now open for questions. So please type them in the chat or mention you want to ask a question. So while we are waiting for questions, I have a couple.
Raju, do you see the raised hands in the?
Let me see, because I usually am notified, but are there raised hands? Oh yes, I'm sorry. Okay. So I'll okay. So let me just ask a quick question, and then I'll go to the. One of you mentioned, I don't recall who, saying that you get this linear mode divergence in any number of dimensions. So I was wondering about why that's the case. Or did I misunderstand?
No, you're absolutely right. It's because the Goldstone bosons have zero energy at non-zero momentum. So it reduces to effectively a one-dimensional problem. Say you have integral d3p, then the momentum is near p naught. So it becomes p naught squared times the difference of p minus p naught. So yes, you're absolutely right. It happens in any number of dimensions.
Okay, very good. Okay, so let me go to Chun Wang. Chun?
Yes. Thank you, Rob. Very nice talk. So my question is about, can you explain a little bit more about why you introduced the higher derivative terms? What's the physical reason?
The physical reason is that they're necessary to stabilize the theory, and in soluble models they do arise. But it's basically for stability.
So are you dealing with the 1+1 dimension or 3+1 dimension?
But in both cases, in 1+1 dimensions, you can solve the theory and show they arise.
Okay.
And in 3+1, you would we would assume that you construct an effective theory where they have to be there.
But normally one would introduce the 5 to the 4th or 5 to the 6th power. So I mean, compare you in order to stabilize the vacuum. I think you can add the higher order term instead of a higher derivative.
No, it won't stabilize because just think of the dispersion relation. It's minus p squared, so the bottom just falls out. You need higher spatial derivatives.
Oh, I see. So
yeah, you stabilize the potential, but not the derivative terms, and that's why it likes to tend to form these spatially inhomogeneous structures, because that term is negative, and so it's going to want to condense about some non-zero momentum.
Okay.
Okay, Peter, was that your hand from before, or is it?
Yes, I mean, maybe a question to Fabian and Rob. I mean, I asked Rob again, or asked Rob, and now I'm asking Fabian. I mean, when you do FRG, I mean, was it expected that you get smaller than zero? The first time I see, I mean, I kind of remember that in FRG people get Z, which is larger than 1. But it's that the fact that at finite mu b it becomes smaller than 1. I wasn't aware, and I was wondering what causes I mean, first of all, the decrease in Z, and then eventually that it becomes negative.
Yeah, so no, we weren't expecting this. First, we thought that there was something wrong in our computation, but then it turned out to be quite persistent. So the thing is that you always have to sometimes you can only see what you allow for to happen. For instance, the phase diagram I've shown, I've only allowed for homogeneous condensates. So even if there would be some inhomogeneous phase somewhere, we wouldn't see it because we only look for homogeneous condensates. And similarly, what we previously never did is to actually look at the momentum dependence of the wave function renormalization. But what we saw in this computation, and somehow in the models, this didn't show up. When you define it at vanishing momentum, then it's really just the Z that we've shown in the dispersion relation. It just becomes negative. And that's Rob kind of, I mean, it's somehow, I guess, some non-trivial, non-linear effect, but in the sense it's, as Rob said, something that just occurs from the fermion loop at large chemical potentials.
But I mean,
But it's
how the fermion loop appears in FIG? It's quark coupled to the meson fields, or is it baryons?
In this case, it really shows up in if you wish, in a 4-quark correlation function in the pion and sigma channel.
Mm-hmm.
So it's a momentum-dependent correlation of a quark anti-quark pair going into a quark anti-quark pair in the channel where you have the quantum numbers of a pion and the sigma. But in this case, it's since it was, I mean, you remember it was above the phase transition, above the crossover. So we were I mean, it's a crossover, okay, but we were kind of in the symmetric phase, and there you see it in these four quark correlation functions.
Mm-hmm. Okay, thanks.
Okay, so the next question is from Bernd Müller.
Hi. First of all, thanks both speakers for giving very clear talks. I have two questions, one for Rob and one for then the second speaker. Let me begin with my question to Rob. And this follows up on Thomas Schäfer's question. In the traditional hadronic description of the interaction of pions with dense baryonic or nucleonic matter, the condensation of modes of non-zero momentum comes about because of the p-wave interaction of the pion field with nucleons, which of course is stronger for finite momentum than for zero momentum. Now here, it doesn't appear in the interaction term, but the condensation, the negative Z appears in the kinetic term. And so my question is, what really, is this ultimately a reflection of the p-wave interaction of the pions with quarks or nucleons, or is it something very different?
I believe it's similar. Actually, it's easy to understand. For example, why do you expect to get a critical endpoint? You consider a coupling of, say, 4 sigmas with a fermion loop. And then at non-zero mu, that can go negative, including the contribution of zero temperature. Similarly, for Z negative, you have a propagator of a pion with a quark loop, and that can go negative. So I believe it's equivalent to the standard Overhauser-Migdal analysis.
It would be very nice to actually see an analysis of this, because it would clarify, better where this comes from and whether it's generic or whether it is something that is subtle and potentially fragile, right? Now my question.
Well, but I think there the 1+1 dimensional models are a very nice example, because there you can just beat it. It's asymptotically free and you can beat it to death.
Yeah, but in the 1+1 dimension, there's no p wave.
Yeah, okay, fair enough.
So,
fair enough. Yeah.
So
okay.
that's why I'm not sure the 1+1 dimension can really help here in that respect, right?
Fair enough.
Right. Now I have a question to Fabian. There is another mechanism that actually in a heavy ion collision creates a favorable emission of particles with finite momentum, and that is simply transverse flow, because that favors particles with a momentum equal to the flow velocity times their mass. Now, and we know that the flow velocity is very significant. So it could be a fraction of the mass. In the case of pions, it would be in the range of 50, 60, 70 MeV. In the case of protons, it would be even larger. And that, of course, has a perfect direction, whereas the mechanism that you have outlined is isotropic in some sense. It doesn't care about the direction of flow. Nonetheless, it's not clear to me that it's easy to distinguish. Now, with the flow, let me finish. With the flow, there is a mechanism that actually preserves any flow that's generated through the expansion, and that is simply momentum conservation. And so my question here is, if this mechanism works not at the boundary, but further inside, is there a conservation law or some mechanism that preserves the enhancement as the system further expands and ultimately breaks up?
Well, I mean, momentum conservation would also apply in this case. So I guess then just disentangling the effects would be, I guess, the difficult part.
Well, I mean, there was a similar question earlier about, whether the yields are different as a whole, the integrated yields. And my sense, and maybe you can comment in relation to Bernd's question, this earlier one, is whether I would expect the entropy to be different in such a phase, and that should give a different total yield for the total number. Would you agree with that?
Yeah, I agree. We haven't looked at the thermodynamic kind of consequences yet. So that's something we are working on. So far, the only thing we know is the correlation function, if you wish, but thermodynamics we haven't looked at. But I would think so, yes.
Right. So that would be one way to add more substance to the signature. There's a question in the chat from Hui Chao, which I will read. Can you remind us how much of the percentage of the enhancement of particle spectra with without mode stage, if it's large enough, it should survive hadronic evolution, right? Is there anything abnormal observed in the particle spectra at RHIC BES?
Whether, to give it really to attach a quantitative number to the prediction, we would need to make a quantitative computation. But I think there has not been a signal yet, but as Rob has also pointed out, these spectra, you would need really good resolution at lower momenta, right? I think if you would get data from, say, you have good resolution from, say, PT of 50 MeV upwards, maybe then you might have a chance of actually observing. We can be super unlucky and they would be buried at 10 MeV or something like that, right? But maybe, and I don't know how realistic it is, but I have heard that experimentalists are incredibly clever when it comes to this, that you actually might be able to measure these spectra down to, say, 50 PT. And then it could be, then there would be a good chance to actually see something like that. But it's important to go to low PT. So if you have spectra that start at a couple of 100 something, then it's unlikely that you would see these signatures.
The next question is from Weiji Fu.
Hello?
Yeah, go ahead.
Okay, thank you, Raju. Just a comment or reply to the questions. What's the physical reasons of the elliptic Z? And recently we found that the elliptic Z come from the London dampings of a quark and antiquark at high chemical potential.
Is there a physical way to connect the Ramsatian constant to Landau damping? How do you think about that? You want to comment?
Well, there's always a Landau damping contribution because
right. That I can understand.
Yeah,
but
this contribution is becomes selective at high mu B.
Fabian, do you want to comment?
Yeah, I just wanted to say, because these more general dispersion relations arise if you look at a more general momentum-dependent propagator. And then if you say you would analytically continue this and then look at the spectral function, and then you can connect this to something like Landau damping very directly.
Okay, so the next is from Nu.
Yes, I have two questions for Fabian's talk. One is about enhancement in the spectrum. You showed one peak. Is it possible there are multi-frequencies and you don't really resolve into one peak, just enhancement in the broad range? Because
since there's only one minimum, there's only one peak. I mean, that would be a situation where you have multiple minima in your dispersion relation. Then you would have some interference of multiple peaks, I guess. But as long as it's just one well-defined minimum in PT, you get one peak. And that's kind of, it's not a sharp peak, even if you have because it's just washed out, because you boost and there's not a uniform fluid velocity, right? So you boost with different velocities the location of this peak, and then you get a little bit washed out peak.
Okay. Then what determines the location of the peak?
And that's the detail of the model, if you wish. It really depends then in terms of how large in QCD the parameter Z and the parameter W would be. That kind of determines where the peak sits. That's the location of the peak. And then how pronounced the peak is depends on how large this energy gap in your dispersion is. So the smaller the energy at the minimum, the larger would be your peak. And that's kind of very intuitive, right? Because then it's even more easy to produce these particles.
Right. Okay. Thank you. I have second question.
Go ahead.
With the two particle correlations. You said you use a Gaussian approach. I'm a little bit, I cannot follow, because when we look the critical point or phase transition, we look actually for long Gaussian fluctuation.
Yeah.
And here you talk about Gaussian. What is the difference, and what are you talking about here? So, yeah.
Yeah, I mean, the difference is, I've indicated this. I mean, at a critical endpoint, you have really long range correlations in your system, right? That's the whole game about the critical endpoint. Now, in this Moat regime, it is a disordered phase, so there are no long range correlations, and that's why. I mean, of course, you always have to scrutinize, but there it's actually, I guess, justified theoretically to start from short range correlations and small fluctuations. So it's really different physics, because it's not as for critical endpoint, no long range fluctuations.
So the width of the Gaussian would be the size of your patches then. So there would be a characteristic correlation length.
Yeah. Okay. Yeah. If you. Yeah.
I see.
Right. That would be. Yeah.
So if I take this as a pion, as pions, do you recommend we measure pi plus, pi minus, or we measure the same sign, pi plus, pi minus, because they are not complicated. Their final state interactions may wash out or cover this measurement. What is the suggestion?
Yeah.
Are we talking about one sign, one particle, one kind of particle, or different correlation? Yeah.
I think I would assume it wouldn't matter. Maybe it's safer to look at the same particle correlations, but that's actually a good suggestion to look at this in more detail. I mean, we haven't done this. I wouldn't think it matters. It's just where you get, where you can go to the lowest PT with the highest statistics. That's, I guess, how I would look for that first. But in detail, I can only guess. Yeah. But that's actually a very good suggestion to look into. Yeah.
I mean, in addition to the yields, distributions, and correlations, I mean, they would also be, in principle, some effect on the flow, right, and the transport properties as well.
Yeah. I think there are a couple of things. Yeah, other things you could consider with just because you have this modified energy dispersion. I think that's kind of the whole punchline is you look for something that is sensitive particles having some minimal energy at a finite momentum. And I would think there are also other effects that.
Yeah, because
and a flow is a good example. Yeah.
Experimentally, perhaps two-particle correlation is easier. But then, for example, same sign, we have a Bose-Einstein effect at a relative zero momentum. For opposite sign, we have a resonance state, for example, K short. That's all appears in this correlation function. So.
Yeah.
Okay. We
Thank
still
you.
have, in principle, time for more questions or comments. I think people may be getting tired. It's late in China and Japan. So anyway, let me again take this opportunity to thank both Fabian and Rob for this really very nice pair of talks. And thanks everyone for attending and the organizers. Okay, so goodbye, everybody.
Thank you very much.
Thank you.
Yeah, thanks a lot for having us.
Yeah, thanks for the invitation. Enjoyed it. Good questions.